Okay, and so now I would like to introduce the next speaker. It's Pedro Antonio Muniz Martins. He's a student at the Universidade Campinas, and he'll talk about separating invariant for two-dimensional orthogonal groups over finite fields. Please, Pedro.
Thanks. I want to thank you by the invitation. And the title of my talk is Separating Invariants for the Two-Dimensional Orthogonal Groups over Finite Fields. I will talk about separating invariants, and let's start with a couple of definitions. Here we consider a finite field with characteristic P, and V is always a n-dimensional vector space over this field F. Here we have our coordinate ring, and everyone knows they become a G-model with the action of the group. I don't think I need to talk about the definition of polynomial invariants, but it's here if anyone needs to refresh their memories. And okay, separate invariants is where we work. And in 2002, Derks and Kemper introduced it as a weaker concept than generating invariants, and the definition is here. And we consider the separate invariance to be minimal if it is minimal with respect to inclusion. Okay, let's talk about the orthogonal group. Consider F key a finite field with characteristic 2 and a vector space, a two-dimensional vector space over this finite field. In this case, we have only two orthogonal groups for our vector space, O2 plus and O2 minus. Here in this talk and in our paper, we just consider the case where O2 plus. And the definition of this group is quite simple. We just consider these two matrices sigma alpha and tau alpha, and or for all alpha in our field without zero, and our orthogonal group is the group formed by all these matrices. It is clearly to see that our orthogonal group is really just generated by sigma 1 and tau alpha for all alpha in our finite field without zero. Okay, now let's talk about the invariants of this orthogonal group. We consider the coordinate ring of this vector space, m copies of this vector space as above, and here we consider xy and yi be elements of the dual of our vector space, because we need to consider they as functions to really calculate our polynomials in a vector from the vector space. And the action of O2 plus over our coordinate ring is given by this table here, where sigma 1 just permutate xy and yi, and tau alpha just multiply our element by alpha minus 1, in the case is acted in xy, and just multiply yi by alpha. This is for all I between 1 and m, and for all alpha in our field without zero. For short, let's make a few definitions here to simplify the result above. We write m dash, the set of numbers going to 1 to m, and we pick a I dash, a tuple with m elements, and we, for short, denote the norm of I dash, the sum of every entry of our tuple. Now we can consider orthogonal invariants. These sets N, U, B, and D, all invariant sets from our invariant algebra. And last year, if I remember right, Shen could find this result that N union B union D is a minimal generating set for the algebra of invariants for an orthogonal group. Consider m copies of the space we want. But in this article, he don't care about separating invariants, and this is our main goal: find a separating set, a minimal separating set in this case. And here we made more definitions to state our results. Here we denote sigma sep as in the last presentation, the minimal integer beta sep, such that all polynomials of degree less or equal to beta sep is separating for our invariant algebra. And we denote sigma sep, the minimal number m0, such that some expansion of a separating set S for our invariant algebra, considering m0 copies of the space, produces a separating set for our great greater invariant algebra, consider m copies of the space, where m is greater or equal to m0. Then, assuming f key a finite field with characteristic 2, we could classify every orbit of our vector space under the action of the O2 plus group, and with this result, we was able to describe a minimal separating set for this invariant algebra, consider m copies of the space we want. And as corollary of these results, we could describe the sigma sep and beta sep for this invariant algebra. We will talk about more, we will explicitly define expansion later when we talk about this result. Here are our theorem of classification. Here we have all the two orbits of the action of group in the vector space, and we call them O2 plus canonical the elements that one group has one and only one element of this type. Then here we have all the orbits of this group acting on our vector space. Again, considering m copies of the space we want. Using this result, it was possible to finally try to describe a separating invariant for this invariant algebra. Here we will denote tau m, the following set consisting of ny, ti, uij, and hij, where I between 1 and m, and I and j between 1 and m, but j is always greater than I. And we can consider, just for simplification, a subset of this set. We will call it tau m2, the following subset, where we just don't pick the elements h, I, g. Okay, with this sets tau m and tau m2, we could find this theorem that, assuming f key a finite field with characteristic 2, the set when our field has just two elements, tau m2 is a minimal separating set for this invariant algebra, and when our field has more than two elements, tau m is a minimal separating set for this invariant algebra for m copies of the space we want. It's interesting to see that the set that Chen found that is the generating of this invariant algebra is greater than our set here, because for generate all the invariant algebra, we need to consider the permutations of hij, hgi, but here we have j greater than I. This make our set a little bit small, really small, than the set that Chen used to generate the invariant algebra. With this theorem, it was possible to find the two corollaries. This is one that using this is really clearly to find the beta sep for this group. When our group just have two elements, the beta sep for this invariant algebra is clearly 2 because of the structure of these polynomials here that make the minimal separating set. And when we have more than two elements in our group, the beta sep for this invariant algebra is just key minus 1. Really, again, it's easy to see just seeing the structure of tau m. Now let's talk about expansions. Here, let's assume V n-dimensional vector space over a field F, and let's talk about the coordinate ring of V, m copies of V, as here. When xig is an element of the dual of Vm, and we define the action of this element in our vector from our vector space like that. Then we can define an m-admissible tuple as a tuple with m0 elements, such that the entries of this tuple is all increasing. And for any m-admissible tuple, we can pick a polynomial f belongs to the invariant algebra and define a new polynomial invariant for our great invariant algebra with m copies as a result of the following substitution. Is clearly in other words, we just pick up like a polynomial in 3 variables, x1, x2, x3, and create another polynomial invariant in 3 variables again. We just make this polynomial be to x4, x5, and x6, and preserve some kind of structure of the polynomial. Then we can define the expansion of some set of invariants. We pick a set S, a subset of our invariant algebra, consider M0 copies of the space, and we can define its expansion. S, we pick every polynomial in our set S and make and put this powered I dash in here to make another polynomial invariant, but for our greater invariant algebra. And refresh the definition of sigma sep. The sigma sep is the minimal number M0, such that this expansion of some separating set S produces a separating set for our for our for our new invariant algebra with more copies of the space. And assuming the characteristic of our field is equals to 2, we could prove that the sigma sep for this invariant algebra is really just equal to 2. And this is really good because just confirm our results, then we can this result that we just need to consider the case where we have two copies of the space, and if we could find a minimal separating set in this case, we can just make an expansion of the set and obtain a minimal separating set for any copies that we want. It's just this. Thank for the attention, and okay, here are some references if anyone is interested more in the topic, and thank you.
Okay, thanks a lot for your talk. Are any questions or comments? So there was a question, what is expansion, but it was explained, yes, during the talk. Pedro, can you show your slides? Yes.
Oh, of course.
Yeah, because now we have, yeah, it's better to keep this way. Are any questions? Okay, then I have a question. So here, minimal separating set was obtained, which is much less actually than generating minimal set, which was known before. And so the question is the following one. Do you have any idea, or maybe just some intuition, when this minimal separating set actually contains minimal possible number of elements?
I
Because
made some calculations, and this set that we found it's really far away from being the with a minimal number of elements possible. I think just when we have one copy of the space and a field with four elements, the minimum possible contains just two elements. It's really small, and our set just have maybe four elements.
okay. Okay, are any other questions? Then let's thank the speaker again.
Thank.
Okay. And now